Okay, so for part 2 of homework 4-3 here, pick up questions 9, 10, and 11. So question 9, well the whole point of this question is to illustrate the purpose of the dot product, right? So they give us a vector here that represents the force, they give us a vector that represents the displacement, right, the position. And the whole point of doing our dot product again is the dot product of the force vector times the displacement vector is the work done. So that process of doing the dot product between those two takes care of the fact that we don't necessarily know the angle, right? So we've seen the equation where it says the force times the displacement equals this, which we hopefully recognize that this is just the work. So then if I do the mathematical process of the dot product, which is again just taking my x component of the force times my x component of the displacement plus my y component of the force times the y component of the displacement, that will equal my work. So again, all I have to do is the dot product, so 12 times 13 plus the y components there, so negative 10 times 11. So obviously at this point it's just a matter of calculating those numbers. We should get 156 minus 110. Obviously I know a lot of you guys probably just put the whole thing in your calculator, and you get 46 joules of work. So if you were to figure out the forces and the angle between them, you would get this same exact number. So anyway, hopefully nothing too tricky on that one. So this one's a good example of illustrating what we do, right, if there's a non-conservative force like friction, right? So friction, which we know uses up energy, it converts energy to thermal energy, but they ask us how much work is done by friction. So they are indicating not all of the work done on this box will convert straight to kinetic energy. But that is the route that I'm going to take to start off with, right? I know that the net work, whatever the total work done on this box is, that's going to cause a change in energy. And because the potential energy is not changing, right, we're not going to a different height, there's no springs involved, so the only change in energy would be kinetic energy. So again, whatever the net work done on the box, that's going to cause its change of kinetic energy. Well, I'm going to use that relationship backwards because they give me the mass here to work with, right? And they give me the initial and the final velocity. So I can find my change in kinetic energy. I can find my final kinetic energy minus my initial kinetic energy. So I'll do that. So 1/2 mass times the final velocity squared minus 1/2 mass times the initial velocity squared, right? So again, just plugging in the measurements I've got, 1/2 of 20 times the final velocity of 2.6 squared minus 1/2 of 20 again times the initial velocity of 0.5 squared. So finding that change in energy ends up being about 65 joules, about 65.1 joules if you want to keep it there. So anyway, I've got 65.1 joules. That's my change in energy, and therefore that's also the net work done on the crate. So I know that a positive 65.1 joules of energy have been done on this crate. So then how does that help me find the work done by friction? Well, the key is I know that there's two forces acting on this crate. Right? There's the force P, which I'm exerting, and then obviously they're implying that there's some friction working against us. So I know that the net work is going to come from the work done by force P minus whatever this work done by friction is, or plus whatever the work done by friction is, but obviously the work done by friction will be a negative number, right? So anyway, I need to find the work done by force P, and then that helps me find the work done by friction, because I know that the net force is 65.1. So if I can find the work done by force P, I've got it. Right, so let's do that. To find the work done by P, well, they give me the force, right? They give me P as 160 Newton force. So I know the force is 160 newtons. I know the angle, and I know that I just want the cosine component. And I know that it goes 8 meters, so I know my displacement. So just plugging all of that in, I've got 160 times cosine of 30 times 8. Again, just using the cosine component of my force P. So then when I find the work done by P, that ends up being about 1,109 joules. So if you round it off, it's 1,109. You could obviously round it more or less than that, and that's fine too. But I'll go with this. So then again, plugging that into my equation, I know my net work is 65.1. I know the work done by P is now 1,110 or 1,109 joules, wherever you want to leave that. And then the work done by friction, again, I know this is going to be a negative number for right now, though I'll leave it as a positive, just to illustrate that once I subtract this over, it very clearly is a negative number, right? So 65.1 minus 1109 ends up giving us about negative 1044 joules of work, or somewhere in that ballpark, right? Negative 1040, negative 1045, depending on where you've rounded things. Any of those answers would be fine. But that would be the work done by friction. So in this case, again, that's the route that I would take. The reason we had to do that, the reason we couldn't just do the work done by friction, right, equals friction times displacement, is because they didn't give me any means of finding the coefficient of friction, right? However, this question could be pretty easily extended. What if instead of asking you to find the work, what if I had asked you, what is the coefficient of friction? Well, you know this was the work done by friction. You know the displacement, so you can find the force of friction, and then from the force of friction and the normal force and the force of P, you could then find the coefficient of friction. So I would expect you to be able to do that too if you needed to. And maybe if you want to review as we get closer to the test, it wouldn't be a bad idea to practice that just to make sure you can find the coefficient of friction if needed. Okay, so then the last question here on homework 4-3. One of really the only new questions we've seen in this section, or at least in this homework assignment. So they give us a spring that does not just follow Hooke's law. So the idea here, the reason they call it an unusual spring is I cannot just use force equals kx. I cannot just use the energy equals 1/2 kx squared. Because it's not a typical spring, those two formulas that I would normally work with go out the window. So instead I have to use this function that they give me. They give me the force equals, I'm going to drop the units just to make it a little bit clearer, but the force equals 2x plus and then just 1x squared, right? So 1x squared, or just obviously x squared, right? Where x is the distance it's been stretched from its equilibrium length. They give me the mass. They tell me it was originally released from 1.5. The object slides over a frictionless horizontal surface, which is nice. I know in fact that there are no other outside forces acting on it. How fast is it moving when the spring returns to equilibrium? Well, the key here is I am really just thinking the work done by the spring, the amount of work, the amount of energy transferred by the spring is going to relate to the kinetic energy that it reaches at equilibrium. The reason that I'm thinking work is because they just gave me force as a function of displacement. And if I'm thinking graphically, and that's what I want you guys to be doing a lot of times, particularly when you get stuck on this. So if I'm thinking graphically, if I've got force versus displacement, I know obviously this would be a quadratic, so it'd look maybe whatever, something like this, but that's not as important as the fact that if this is a force versus displacement graph, then the work, the energy, would be the area underneath the curve, or in other words, the work would be the integral of this function, right? So in order to find my work or energy, I need to integrate this function. So again, if I want to find my work done by the spring, which is exactly what I want to do, I'm going to integrate the function with respect to dx, with respect to the position. So I'm going to integrate both sides of my original function up there. So integrating both of those with respect to x. Well, it's a pretty easy process, right, hopefully for us to do. So again, the left-hand side, the integral of force with respect to dx is my work. On the right-hand side, when I integrate that, becomes a power of 2, and then I divide by 2, right? So it ends up being 1 x to the second plus 1/3 x to the third, adding 1 to that, making that a 3, and then dividing by that new power of 3. I do also have the plus c, right? I do also have the plus c, but then I know the bounds that I'm going from. I know that I'm going from an original, right, of 1.5 to 0. So however you want to do that, I might call 1.5 the ending just because that's going to keep it positive, and 0. It doesn't really matter as long as we realize that the energy here, whatever this energy is transferring to the kinetic energy. But anyway, so I've got these measurements to work with. So all I'm going to do now is plug in both of those numbers. So the work for 1.5 would just be 1.5 squared plus 1/3 times 1.5 to the third, right? Plus my c, which I don't know. But then I'll subtract when I plug in 0. Well, obviously 0 is easy to plug in. 0, 0, and then my plus c. And so that's where the c takes care of itself. I don't need to know what that constant value was. I just need to find out the work done, which would just be the change of work here, which would just be 1.5 squared plus 1/3 times 1.5 to the third power. So my work then ends up being about 3.375 joules of energy. And again, the big concept I need to be comfortable with is the amount of work done by the spring. So this 3.375 transfers to the kinetic energy of the block, right? Because we're reaching equilibrium position, we know that that energy has transferred to the kinetic energy of the block. The good news is, even if it wasn't equilibrium, I would have just changed this bound to be whatever position they asked me to find. So if they asked 1 meter or what have you, I would just change that number. But anyway, finishing this out, I've got 3.375 equals 1/2 mass times velocity squared. Well, they gave me the mass of 3 kilograms, so it's just 1/2 times 3 times velocity squared. So my velocity squared ends up being a convenient 2.25 squared there, and then square rooting both sides, I get 1.5 meters per second. So the velocity of the block when it's in equilibrium position is 1.5 meters per second. So again, question 11, probably one of the few questions on here that's new to us, right? Hopefully one of the only questions that maybe gave you any trouble. But as soon as you hopefully realize that we're doing force versus displacement, and therefore the area, the integral, is the path that we want to take, hopefully this question wasn't too bad to solve the rest of the way. But anyway, that finishes out homework 4-3. If you did have any questions on this type of stuff, if there are any of these that you're shaky on, come find me so I can help you get some more practice, but otherwise, hopefully it wasn't too bad.